Good afternoon, everybody. I think still there is a lot of audience outside, but we have to start on time. So I hope you had a great lunch. I would like to thank Prof. Fatimi for inviting me for the second year as a chairperson. I'm inviting now Dr. Neelke Munck. She is working in IVF Center currently as a scientific advisor at IVI Middle East Fertility Clinic in Abu Dhabi. She works as she is studied a biomedical science and molecular medical biotechnology at Belgium. For the last 8 years, she has been working as a clinical embryologist at the Center for Reproductive Medicine at Brussels, UZ, where she obtained her PhD on safety and efficiency of oocyte vitrification. After her PhD, her main research topic were improving embryo culture condition and embryo development. She's going to present for us the hidden effect of oocyte vitrification, which is in deep of her experience. Thank you.
Good afternoon, everybody. So my talk today will be about the hidden effects of oocyte vitrification. So as Christmas is approaching, I thought I could start with a nice picture of the snowflakes and a Christmas tree. As you can see, the structure of the ice crystals of the snowflakes are very nice because the hydrogen, the oxygen molecules, they bind very nicely. Of course, when we look at vitrification, of course, we don't want those ice crystals. Because when you look at the cell membrane and how the molecules are disorganized in the liquid phase, you can see that once the ice crystals form, they may rupture membranes. While during the vitrification, we want to obtain the molecules in a disorganized way, while the liquid will behave as a solid. Now, what is important to obtain this vitrification? There are three things that are very important. That is an increase in the viscosity, high cooling and warming rates, and the volume is also very important. So first, the viscosity. We can increase the viscosity by plunging the oocytes in medium containing penetrating and non-penetrating cryoprotectants. So the non-penetrating cryoprotectants, when you put oocytes in a solution containing the penetrating cryoprotectants, in a first stage, the oocyte will dehydrate because water moves faster than cryoprotectants, so the water will get out of the cell. Afterwards, the cryoprotectants will move in, so the cell will rehydrate. Most used penetrating cryoprotectants are DMSO, ethylene glycol, and propanediol. Then we have the non-penetrating cryoprotectants, so they do not penetrate the cell, and they will lead to dehydration of the oocyte, and they will also stabilize the membranes. Then the cooling and warming rate, they are very important to have a very high cooling and warming rate. So when you look at a phase diagram of a hypothetical aqueous solution, you can see that above the melting temperature, you have a liquid phase. And then below the melting temperature, you have a high risk of ice crystal formation. So during vitrification, we want to avoid the cell to become in this phase. And then depending on the CPA concentration, the glass transition temperature can be reached in which your liquid will form into a glass. So the faster you move through these phases, so with a high cooling rate, you will prevent ice crystal formation. And then during the warming, it is very important that you warm fast, because once you go above the devitrification temperature, you have a possibility of recrystallization, so where small ice crystals can recrystallize. Another thing that is important is the volume that you load on the straw. So if you use a bigger volume, this will also lead to lower cooling rates. Here I show some different devices that can be used for vitrification. These are open devices in which the oocyte is immediately exposed to the liquid nitrogen, so they will have a very high cooling rate, while these devices are closed devices, and they, on general, have a lower cooling rate. And here are some vitrification media. So there are many media on the market to vitrify oocytes. Now, the question of this talk is, in fact, how safe is oocyte vitrification? And with this, of course, we want that the transfer of an embryo that is derived from vitrified oocytes leads to the delivery of a healthy child. So when you look at the oocyte, during the warming procedure, you can clearly see that it's going through some chemical and physical stresses. And you wonder, of course, that the oocyte that is survived at the end, if the structure of this oocyte is still good. Especially if you look at all the organelles that are in the oocyte, you may wonder how the vitrification affects their structure. So this is what the talk will be about today. So we will compare the effect of vitrification by comparing fresh and vitrified oocytes and by looking at studies in which different devices were compared. So for the oocyte, I will focus on these topics, then a little bit on the embryo and also on the neonates. So first of all, the spindle. So as we all know, the spindle is very important to obtain fertilization, and it's also important for the further embryo development and the blastulation. Then it will also determine a correct ploidy of your embryo and hence have an effect on the implantation. So there are different ways by which you can analyze the spindle. One of them is with pulse scope analysis, which is very nice because it's a non-invasive technique and you can so you do not have to sacrifice the oocyte. In this study, they looked at different warming methods at room temperature or at 37 degrees. And as you can see, when the procedure is performed at 37 degrees, the spindle is maintained. Another way to look at the spindle is with confocal microscopy, in which you can see the tubulin here in green, and in red you can see the chromosomes. So in this study they compared fresh and vitrified oocytes, and as you can see, after in fresh oocytes, most of the oocytes maintain a nice bipolar structure and the chromosomes are mostly aligned, while vitrification leads to more disturbed patterns in which sometimes even the spindle is completely absent. So they concluded, in fact, that the bipolar organization of the spindle is mostly maintained after the vitrification procedure, but that there is a compromised chromosome alignment. Then the vacuoles. So as you can see, this oocyte has many vacuoles. So they're empty structures that are surrounded by a membrane. Normally they're only present in less than 5% of the oocytes, and they have been shown to affect embryo development. Especially the later they appear during the development, the more impact they have on the development. A nice way to look at vacuoles is with electron microscopy. Of course, with electron microscopy, we will see more vacuoles than we will see with light microscopy. So in this study, they looked at the vacuoles in fresh oocytes, vitrified and slow frozen oocytes. As you can see, fresh oocytes also display vacuoles, but after vitrification, there is a doubling in the presence of vacuoles, which is even much worse after slow freezing. So there is a high proportion of oocytes, with vacuoles. And in fact, this is important because the vacuoles, when they are present, they lead to an inward organelle displacement, and they impact, in fact, the other structures that are present in the oocyte as they move them inwards, and they move them to positions where they are not needed. Then the microvilli and the cortical granules. So the microvilli, you don't see them in this picture, but they are present here, and they are important for anchoring the sperm to the oocyte, and hence very important for the fertilization. And then the cortical granules, they are present in the subcortical region, and they are derived from the Golgi apparatus during the maturation of the oocyte. Once the sperm penetrates, they are responsible for the cortical reaction, which will prevent that multiple sperms enter the oocyte by the initiation of the zona hardening. So in this picture, you can see a fresh oocyte and a vitrified oocyte. And for the vitrified oocyte, you can see that there are some electron-dense microvilli present, but in general, they could see that in 30% of the oocytes that they analyzed, there was an abnormal microvillar structure. Most of the time, the oolemma was even flat with only small blunts of microvillar structures that were present. Then for the cortical granules, here you see a fresh oocyte and a vitrified oocyte. So in a fresh oocyte, normally you see a rim of cortical granules that is present in the subcortical region, while after vitrification you see that the amount and the density is much lower. For this reason, and because of the affection of the microvilli, it is advised to perform ICSI after oocyte vitrification rather than IVF. Then the mitochondria. So the mitochondria, they are the most abundant organelles in the ooplasm. They synthesize ATP, which is needed for the oocyte. And normally the microtubules, they move them to places where high ATP is needed. Now, as it is thought that the mitochondria only start to replicate after the blastulation rate on, it is very important that the oocyte starts with a correct pool of mitochondria. So in this study, you can see that they looked at fresh, vitrified, and slow frozen oocytes, and you can see the degeneration of the mitochondria, which was present after vitrification and even much higher after slow freezing. And in this picture, you can even see that in the subcortical region, there are not even mitochondria and vesicles present. So vitrification, normally the mitochondria and vesicles should also be present here. So the vitrification shifts the organelles indeed to different positions. Another way to look at the mitochondria is to look at ATP concentration. So in this study, they looked with a bioluminescent assay at the ATP levels in which light is generated, and the amount of light that is generated will reflect the ATP concentration. So they compared fresh oocyte with vitrified oocytes, and as you can see, after 3 hours of incubation, the oocytes have a restored ATP level. And for this reason, most of the centers perform ICSI 3 hours after the warming procedure. Then another way to look at the mitochondria is to look at the mitochondrial membrane potential. This is you can look at it with a staining, in which this in the staining it's a GC1 staining, and normally it's present as a monomer. And once there is an increase in the potential, there will be aggregates formed, and then you can see them with a red fluorescence. So in this case, you see a fresh oocyte. And these three are vitrified oocytes immediately after the warming, 2 hours after warming, and 4 hours. And they see that 4 hours after the warming, the mitochondrial membrane potential is restored. Then a study on gene expression. So they compared fresh oocytes with vitrified and slow frozen oocytes. So when you look at fresh oocytes and you compare them with slow frozen oocytes after microarray, you see that there is a high number of genes up and down regulated. Then they also compared fresh and vitrified oocytes, and you can see that even the number of genes that are up and down regulated is even higher. And then they compared which genes were common between both cryopreservation techniques, and you can in fact see that there is only a small proportion of genes between the two cryopreservation techniques that are the same. So both cryopreservation techniques, they affect differently the oocyte. Then also something on the device. So in this study, they compared oocytes with electron microscopy after vitrification with a closed device and after vitrification with an open device. So they looked at the rehydration, the cortical granules, the mitochondria, and in fact the closed device performs less good. So there were higher degeneration of mitochondria, less vesicles, the more cortical granules that already released. So the open device performs better. Then we move on to the embryo. So a study that we performed on the first division, in fact, that happens after the vitrification. It is the completion of the second meiotic division. So the mature oocyte that we receive in the lab is the oocyte that already extruded the first polar body. So it already went through the first meiotic division. Then we vitrify the oocytes, and afterwards the second meiotic division is completed by the extrusion of the second polar body. So what we did in this study is we did a biopsy of the first polar body and of the second polar body after the vitrification to see if it affects the meiotic division. So when you analyze the first polar body, in this case, you could see that the polar body had a loss of chromosome 16, which means that the oocyte had a gain of chromosome 16. And then we analyzed the second polar body, and as you can see, this polar body had a gain of chromosome 16, which means that the zygote itself compensated for the gain in the oocyte. And then there was also a gain of chromosome 11, so it means that the zygote has a monosomy for chromosome 11. For all the oocytes that were analyzed between fresh and vitrified donor oocytes, we did not observe any difference in the aneuploidy rate. Then another study in which they analyzed the aneuploidy rate at the blastocyst stage between fresh and vitrified, in vitrified oocyte, fresh and vitrified oocytes. So they analyzed all arrested embryos, and they could not see differences between the vitrification and the control. And then also for all the usable blastocysts, they did not see any difference between the ploidy at the blastocyst stage. Then a study analyzing the methylation. So you know, during the pre-implantation development, there are major waves of demethylation and remethylation. And this methylation is performed by DNMT enzymes, which put a methyl group on the cytosine residues. And later on, this is oxidized by TET enzymes, which put a hydroxy group. So we performed a staining for methylcytosine and the hydroxymethylcytosine between fresh and vitrified oocytes. And also here, no difference was obtained at the level of the embryo. Then embryo development has also been analyzed between fresh and vitrified oocytes. So in this study, oocytes from infertile patients were analyzed. And the main difference that they could observe was the timing at which the syngamy occurs, which appears to be faster after vitrification. And once syngamy is obtained, the embryos develop in the same pattern between fresh and vitrified oocytes. Another study that we performed, we also looked at the development of donor oocytes after close vitrification, and here we did not see differences in the development. In this study, they also looked at mature oocytes from infertile patients, where they could see that the fertilization was lower, the cleavage, and also the blastocyst rate. And then another study in which donor oocytes were compared after vitrification with an open device. And in this study, they saw that the first mitotic division occurs at least on average 1 hour later in vitrified oocytes. And then in this study, there was a closed device compared with an open device. So except for the fact that rehydration was already different in both devices, in this study we also showed that the cell number on day 3 is also lower in oocytes that are obtained from a closed device. So the open devices, they generate embryos with at least 1 blastomere more on day 3 of development. And then there have also been a few studies analyzing the neonatal outcome after oocyte vitrification. So in this study, donor oocytes and oocytes from autologous oocytes, the pregnancies were analyzed. And as you can see, for the neonatal outcome, there was no difference with fresh oocytes. In this study, they looked at pregnancy complications and the congenital birth defects after fertility preservation, and they also did not observe any case with defects. And in this study with donor and infertile oocytes, also no difference was observed between fresh and vitrified oocytes. So in fact, to conclude, when we look at the oocytes, we see that there are many studies that show that the ultrastructure of the oocyte is affected by the vitrification procedure. When we then look at the embryo, we see that there are less studies that show that there is any difference between fresh and vitrified oocytes. And at the level of the children, it appears that we don't see any effect anymore of the oocyte vitrification. Oh, thank you. Yeah.